Okay, welcome guys. I hope everyone is doing good. Okay, so we're still moving on with our linear algebra lessons. And in today's lesson, we are just going to look at a few problems which cover most of the material that we have done so far, so that at least we can perfect our understanding of the use of the algebraic notation of matrices in doing a lot of things in linear algebra. You see that? So the first thing that we're going to do is we're going to look at a problem which is focusing mostly on the addition operation of matrices. That's what we are going to look at. So a typical question that you might get will be something like this. You see that? Given two matrices A and B of the same order, prove that A plus B is the same as saying P plus A. Then B, prove that A plus B then plus C is the same as saying A plus B plus C. Like that. So this is a problem which is trying to ask us to verify the commutative and the associative properties of addition of matrices. But now what we want to employ the algebraic tools that we have so far developed to see how we can actually get to answer this problem. So what I will suggest is that before you even look at the solution, try to give yourself time and see if you can use all the tools that we have written so far to prove this result. And then afterwards, you can then go on to look at the solution. Otherwise, let's move on and see how we get to solve this problem. So now we want to provide a solution to this problem. So we shall prove first the first part, where we are asked to prove the commutative property of addition. You see that? So now to begin, we'll say suppose A, which can be represented as Aij, and B, which can be represented as Bij, suppose A and B are matrices of the same order. You see that? So let's suppose these two matrices A and B are matrices of the same order and are represented using those given representation. Then what follows from here? So it follows from here that A plus B can actually be defined as Aij plus Bij. You see that? So that's one thing that you should know. That's how we define addition naturally. But if you look at what is inside the bracket, actually, you see that. So when you look inside this bracket that we have here, remember Aij represents a particular entry in matrix A, and Bij represent another entry which corresponds to Aij in matrix B. You see that? But one thing that you should know, entries of what can I say? Entries of all matrices, they always come from a particular field, and most often the fields that we always extract our entries from is that of the real numbers or sometimes the complex numbers. You see that? But for now, in linear algebra, we'll assume that all our entries that you will be dealing with, they are coming from the set of real numbers. If it's not so, we are going to be specific about that. You see? So now, since we know that what the things inside are real numbers, so just to comment, so these are real numbers. So the entries inside the brackets, they are real numbers. So which means if these two things are real numbers and they are being added together, we know from our understanding of real numbers that the addition of real numbers is commutative, which means I can swap Bij and Aij in that order. But now, having swapped Bij and Aij in that order, I can see that I can split this backwards again so that I get Bij plus Aij. But now if you look at what we have here, the first term represents the matrix B and the second term represents the matrix A. So we can see now that the proof is done. So this is how you can go about proving that the addition of matrices is commutative. So this is how it works. That's how you can go about. So we are using algebraic notation and we are exploiting the properties of real numbers without having to prove them. You see that? Because in a proper setting, we don't have to actually assume the commutative property of real numbers up until we've proved that. But now linear algebra is a subject which is based on the fact that real numbers, they always exist and they have all these properties with them. Properties like associativity, they just hold automatically, and also commutativity and many others. So we just assume all the properties of real numbers, they hold true whenever we're performing some linear algebraic stuff. You see. Okay, now we have seen how to prove what we call this, the commutativity of addition. Now let's see about the associativity. Associativity. So we'll say, suppose A, which is Aij, B, which is Bij, and C, which is Cij, are all matrices of the same order. So we are going to assume that. So assume that A, B, and C are all matrices of the same order. So now what follows? So having these as matrices of the same order, we know that A plus B plus C is actually equivalent to saying Aij plus Bij then plus Cij. That's what it means to add up these two matrices. So AB plus C can be written like that in algebraic notation, where we have shown the bracket around A and B by bracketing Aij and Bij. You see that? But again, remember, all these things that are inside these outward brackets, they are all real numbers. So if all these things are all real numbers, we know that from the start of real numbers, that real numbers, they are associative, which means I can remove the bracket that is around Aij and Bij and put it around Bij and Cij, like that. You see? So now I have two different blocks from the ones that I had previously. Now I can separate my two blocks, which will give me Aij plus another bracket of Bij plus, it's supposed to be Cij. But if you look now, what we have here is the first term represents the matrix A itself. Then inside the bracket, we have the sum of B and C. So which proves our result again. Easy. So this is how we get to prove some addition properties using the algebraic notation that we have so far developed. So this is going to be the first problem to look at as a form of practicing our algebraic notation of matrices. So I will end this lesson here, and then we're gonna next we'll do another lesson where we solve another problem again, which involves the use of algebraic notation. Okay, thank you for watching. So see you on the next video. Bye.